Hello everyone, welcome to the lecture 2 of Uncertainty Modeling in AI. And today we are going to look at Bayesian networks, or otherwise known as the directed graphical models. Of course, I didn't invent any of today's material. A lot of slides and content of today's lecture are taken from the unpublished textbook by Michael Jordan, which you can find in this link here. I also took some of the contents of today's lecture from the textbooks written by Christopher Bishop, Kevin Murphy, as well as Daphne Collar. I definitely encourage every one of you to look at the relevant chapters of the textbooks after today's lecture. Hopefully, by the end of today's lecture, you are able to explain the concept of conditional independence. We'll see that the concept of conditional independence it's an extension of the concept of probability independence, which I looked at in the last week's lecture. And we'll also see that the conditional independence concept will form a foundation of graphical model that we will use for the rest of the lectures in this semester. We'll see how to use the Bayesian network to represent or to encode the conditional independence in joint distribution. Then we'll look at how to read off conditional independence by what we call the deseparation concepts using the three canonical three-node graph. And by doing so, we will formally introduce the baseball algorithm, which will allow us to deduce all conditional independence in the Bayesian network. Finally, we'll look at the concept of Markov blanket. The question is that why do we need to study graphical model after we have already looked at some of the rules for probability that will allow us to model a joint distribution, as well as will allow us to manipulate the probabilities in last week's lecture. The reason is because while we have seen those rules in last week's lecture, we have also seen that it becomes computationally intractable when the number of random variables becomes too large in the joint probability distribution. And let us illustrate this with a n discrete number of random variables. Example, x1 all the way to xn over here, which represents n number of discrete random variables, where each one of these random variables will take one out of k states over here. So this means that each one of these can take a state of 1 all the way to k. And in total, we will need a total of k to the power of n parameters to represent this joint distribution of the probability of x1 all the way to xn. Let's look at an example where n here equals to 3. This means that I have 3 random variables where each one of the random variables takes k equals to 2 states. This means that I have a set of binary random variables. And in this particular case, we can see that for x1, x2, x3, to represent the joint probability distribution of x1, x2, and x3, I would need a total of 8 parameters to represent this, namely 0, 0, 0, 0, 0, 1, and all the way to 1, 1, 1. So in total, I will need theta 1, theta 2, all the way to theta 8 to represent this joint distribution table over here. And in fact, to be more precise, I will only need altogether of k to the power of n minus 1 parameter. That's because the total sum of all the probabilities in this probability distribution table should add up to be 1. And hence, I only need 7 parameters over here, where the last one can be found by 1 minus away the total of the preceding 7 parameters over here. And we'll see that inference becomes intractable when this n over here becomes large, which can happen very often in the real world scenario. As I mentioned in our introduction class, that suppose that I'm given an image where every pixel in this image represents a random variable. So in this case, if I have a megapixel image, n could be easily in the order of 1,000,000, and any k states to the power of 1,000,000. This would lead to an astronomical number where inference can become intractable. So an illustration over here, suppose that we are just interested in doing a marginalization of one random variable in this joint probability distribution table. If we have a very large number of random variable where each one of it take one out of k state. By just marginalizing over x1, we'll need to go through all the states over here. So marginalizing x1 is equivalent to saying that I want to marginalize, I want to do the sum of x1 equals to 0 all the way to n plus all the way to x1 equals to k and xn over here, where I need to evaluate this over all possible states of x2 to xn, and I have to sum over all possible states of x1 from 0 to k over here. And in this particular case, what it means is that I would have to, by doing a marginalization over one random variable x1 over here, I would have to assess over all the possible entries in this joint probability distribution table, and this would become intractable, or it means that it's often not computationally efficient in the case where n is a large number. We can see that, for example, in an image, a megapixel image, n can easily be in the order of 1 million. So inference would become a problem. Another problem here would be that huge amount of data would be needed to learn all the parameters. That's because in this particular table over here, we would have altogether k to the power of n minus 1 parameters over here. So in order to fit the distribution, to fit this joint probability distribution to what we have observed in the data, we'll need a large amount of data to make sure that this fitting the parameters in the joint distribution table goes well. So an easy solution would be assume that all the random variables are fully independent, as what we have seen in the last week's lecture. So in this particular case, we'll see that given a joint probability distribution of x1 to xn, if all the random variables are fully independent, then we can factorize this joint probability distribution into a product of all the marginal probability of pxi over here, where each one of these marginal probability can be represented by k parameters. And altogether, we have n number of random variables. This means that we have n times of this k number of parameters. So in total, we will have n multiplied by k number of parameters to let us represent the joint probability distribution of x1 all the way to xn. And in this case, we can see that since n multiplied by k is a lot lesser than k to the power of n, which is in the case of the fully correlated case, then what this means is that inference would become more tractable and a smaller amount of data is needed to learn all the parameters. But the question is that, is this useful at all, to assume that all the random variables are fully independent, despite that we will end up with a much more tractable inference and learning solution? So an example here would be, suppose that I'm given a series of letters PROBABILI, and I ask you to guess what is the probability of the next word occurring, or next letter of occurring in this particular slot over here. So the probability of this, suppose that the probability of this to be y equals to what? Probability. The question that we ask here is that, is this probability of y occurring in this particular slot, is it fully independent of all the other random variables or all the other letters that occurs before it, where we represent each one of these letters as a random variable, x1, x2, all the way to xn, for example. So in this case here, is this particular random variable independent of what is observed, all the random variables that is observed earlier? The answer is probably no, because we know that from the general context that this has to form a word, this spelling has to form a word, and from the earlier observed random variables, we already knew, or it already gave us some hint of what the probability of y should be. So it should be a probability of xn conditioned upon all the other random variable that we have observed earlier on. And we will see that what's the probability of xn equals to y, for example, conditioned upon all these random variable. what is this? And we saw that from this example, it's intuitive that this probability distribution is not going to be independent of what has already been observed. Another example here would be, suppose that I'm given an image where every pixel here represents a state of label, whether this particular pixel should be labeled as water or a sky. Suppose that we are only interested in a binary label of each random variable over here. And further suppose that we observe all the states, all the labels of the green nodes over here where they are labeled as water, for example, and we ask the question, what would be the probability of this particular pixel, this particular yellow node over here? Is it more likely that it's a water, or is it more likely that it's going to take a state of sky? So we know that, as I've mentioned in the introductory lecture, that a pair of pixels, they appear as neighbor not because of pure coincidence. It's because of some relation that is in the real 3D scene. They are likely to be really coexisting as a neighbor in the real 3D scene, and that's why they are being projected into the image as neighboring pixel. So since they are neighbors in the real 3D world, this also means that they are likely going to be in the same object and belong to the same object class. Hence, as a result, if we observe that all these nodes that are neighboring to the yellow nodes as water, then it's more likely that the node is going to be labeled as water as well. Hence, this means that it's not always correct to assume full independence of the random variable. So since we have looked at two extremes where in one extreme end, all the random variables are fully correlated, we saw that it leads to exponential complexity in the inference as well as the learning. And on the other end, if we assume that the random variables, they are all not correlated, which means that they are all independent, then we end up with a linear complexity, which is much more tractable for learning as well as inference. But we also saw that the assumption of full independence led to a drop in the model's usefulness, because in most real-world examples, the random variables are not fully independent. So the question is that how can we now compactly represent the joint distributions so that we can make use of the joint probability distribution to do inference in a reasonable amount of computational time, as well as to learn the parameters with a reasonable amount of data. And of course, the answer lies in the use of graphical model. So we have seen that, as I mentioned earlier, that we have seen both ends of the spectrum, where when we assume that all the random variables are fully independent, then this is insufficient to model real-world problems, because we saw that in the spelling example as well as the image labeling example, that there is indeed a correlation between every random variable with the neighbors of that particular random variable. And if we assume that all the random variables are fully correlated, and this can become intractable because it has the exponential complexity of k to the power of n in terms of the number of parameters in the joint distribution. And of course, an intelligent guess of what's going to happen next would be that we are going to find somewhere in between these two extreme ends. It would be a good compromise by assuming this intermediate degree of independency among the random variable, and this would lead us to the concept of conditional independence. So more formally, given two random variables of xa and xc, we say that they are conditionally independent given b if the probability distribution of xa and xc conditioned upon or given xb is equals to xa conditioned upon xb multiplied by xc conditioned upon xb. So in general case, this is not true where xa and xc, they are not independent. So this factorization here is not true. But in the case when we observe b, that means that it's conditioned, a and c is conditioned upon b, then a and c becomes conditionally independent. Hence, we can factorize them into these two terms here, conditioned upon that we have observed B over here. So what this means is that once we observe B, the random variables of A and C becomes independent or becomes conditionally independent. Alternatively, we can write the probability distribution as the probability of XA conditional upon XB and C is equals to the probability of XA conditional upon XB. This is because once we have observed XB, then A and C becomes conditionally independent. What this means is that once I have seen XB, seeing XC or seeing XA doesn't give me more information of XC and vice versa. And we will write this conditional independence as A, the random variable of XA is conditionally independent of XC, given that we have observed XB. An example of this would be in the family trees, where a node here represents an individual's genotype. For example, in this illustration over here, it's a family tree of the Simpson family. We can see that we only need to observe what is in the parents of Bart in order to give some information about the genotype of Bart. What this means is that by observing the parents of Bart Simpson over here, the non-descendants of Bart, which includes his siblings as well as his grandparents and auntie uncles, all these are the non-descendants of Bart, excluding the parents. It's going to be conditionally independent once we have observed the parents of Bart Simpson over here, which can otherwise be written into this rule over here. The genotype of Bart is conditionally independent of all the non-descendants of Bart, excluding his parents, given that we have observed his parents' genotype. And what this means is that any random variable is now locally dependent on only its parents. That means that if I treat the genotype of Bart as a random variable, it is locally dependent on only its parents, its direct parents, and is independent of all the other non-ancestors, excluding its parents, and this is known as the Markov assumption. So we'll use a directed acyclical graph to represent conditional independence. This directed acyclical graph is otherwise known as the Bayesian networks. It consists of a set of nodes and a set of oriented edges. An example is shown in this graph, in this directed graph over here, where each one of the nodes represents a random variable. So this node here, for example, it represents the random variable x1, x2, and x3 respectively. And the edge over here are all edges with directed edges, meaning that it will point from one random variable to another. And since the graph is an acyclical graph, it means that it cannot contain any cycles. So this means that we can see that example over here, that if we follow starting from any random variable and follow the direction of the edges, there's no way that we can go back to the same starting random variable. Otherwise, there will be cycles. And we'll further use the notation, the commonly used notation in the literature of graphical model, that to use shaded nodes over here to represent an observed random variable. So if I were to shade x4 here, this means that I have observed that x4 is equals to a certain realization value. And we'll leave the unshaded nodes to represent the latent or hidden random variable. What this means is that this unshaded node is not observed. That means that we keep it as a general form. We don't fix it to a certain observation at all. We'll further define the term of ancestors. Ancestors are the parents, grandparents, etc. of a node, and it can be found by a path from the node to any other nodes in the graph. So an example over here, suppose that I'm going to look at x4 over here. I'm going to find the ancestor of x4. So let's me denote this for x4 as t, and I'm going to find the ancestor of t over here, which is x4 in this particular case over here. So here the ancestor of t is the set of nodes S that connects to t via a trail. This means that any path starting from any node here, if I were to follow the direction of the edges and I ended up in x4, this means that the starting node and all the nodes that are in the path belongs to the set of ancestor that of x4 over here. So an example here is that let's look at the example. If I were to start from x1 over here, I follow this path over here, and I can see that x2 is in the path of x1. Hence, x2 and x1, they are both ancestors of x4 over here. A counter example would be if I were to start from x5 over here, and I see that the direction of arrow points towards x6, but it terminates here, so there's no way that I can get to x4. Hence, both x5 and x6 are not ancestor of x4 over here. We can do this for any other nodes in the graph to figure out what are the complete set of ancestors of x4 and non-ancestors of x4. We also define a set of descendants which consists of the children, the grandchildren of a node. And similarly, we can also find this tracing the trails from one node to another. So here, let's denote S as x3, where we want to find the descendants of x3. So the descendants of S or x3, or in this example over here, is the set of nodes that can be reached via trails from S. This means that starting from S over here, I follow the arrows that is from S, and all the nodes that are in this path of the arrows from S, they are they are considered as the descendant of x3 over here. So we can see here, in this case here, it's very simple. x5 is in the path, so x5 is one of the descendants of x3, as well as x6, and it terminates at x6. So in total, x5 and x6 are the descendants of x3, and we can see that this trail here doesn't reach x1, x2, or x4. Hence, x1, x2, and x4, they are not descendants of x3. So as mentioned earlier on, that for every random variable, for every node in the graph, there's an associated random variable which we denote as xi over here. So here, for example, this node over here in the graph, which is in V, 2 is inside the set of V. So x2 it denotes the random variable that is represented by this node in the graph. And for each node, besides the ancestors and the descendants, we also define a set of parents which we denote as pi I over here. So we will represent x pi I as the set of random variables which are parents to the random variable xi, and we can see that the number of parents to any random variable xi can be a null set to any number to infinity. Of course, we don't have infinity over here, because that would mean infinite number of random variables. An example here would be that x1, the random variable x1, there's no parents. Hence, the parent over here we denote as a null set. And another example here where, for example, x4, we look at x4 over here. Its parents, which is the one that is pointing with the arrow pointing towards x4, it's only x2. Hence, x2 is the parent of x4. And we further consider x6. Now, x6, we can see that there are two arrows pointing towards x6 from x2 and x5. What this means is that both x2 and x5 are parents of x6 over here. And we have seen earlier in the example of the family tree of Bart-Simpson that there is a Markov assumption where each random variable, it becomes independent of its non-descendant. So it becomes independent of the non-descendant given its parents. So we can write this in the conditional independence statement where xi here is the random variable that we are interested in, and it becomes conditionally independent. So we use this symbol over here to represent it. It becomes conditionally independent of the non-descendant of xi, excluding the parents of xi, given that we have observed the parents of xi. And here's a general example that in the case of x2 over here, all the non-descendants of x2 are outlined in blue. By the way, the color here, the color of the circle here doesn't mean anything. It's just for the illustration in this specific example over here. So we can see that the non-descendants of x2, they are x1, x3, and x5, where by we can actually trace out the descendants of x2 by following the paths over here, and we can see that x1, x3, and x5 is not reachable via these trails that is from x2, and hence they are the non-descendants of x2. And here, following this example over here, this the general statement over here, we can see that the parents of x2 is x1. So once we observe the parent, then we can say that x2 is conditionally independent of x3 and x5, conditioned upon that we have observed x1 over here. And by following this general rule of the Markov assumption, we can derive, or we can observe, the following set of conditional independence by simply reading off the graph over here. So let's look at an example over here. x1 is conditionally independent of nothing, given nothing, because there is no non-descendant of x1. There's no ancestors of x1, and no parents of x1, and non-descendant of x1. Another example over here would be, let's look at x4 over here. All its non-descendants are, since there's no path towards any other descendants, what this means is that all the other random variable x1, x2, x3, x5, and x6, they are all non-descendants of x4. So following the rule, if we observe the parent of x4, which is x2 over here, so we can say that x4 becomes conditionally independent of all the non-descendants, which are x1, x3, x5, and x6, conditioned upon, given that we have observe x2 over here, and we can verify that indeed this is one of the conditional independence that we can read off from the Bayesian network. Now let's look at another example of x5. We can see that x6 is its direct descendant, and what this means is that x1, x2, x4, and x3, they are non-descendants of x5. And if we observe x3, which is the parents, we can write that x5 is conditionally independent of x1, x2, and x4, given that we have observed the parents x3, which is indeed another conditional independence condition that we can directly read off from the graphical model. So I'll leave all the other examples over here for you to practice on your own. And now we can generally state the Markov assumption that the basic conditional independence statements gives rise to, in the directed graphical model, gives rise to a set of conditional probabilities by following the parent-child conditional independence relation that we have listed earlier. So this directly gives rise to a set of conditional probability, which can be rewritten as the probability of x1 conditioned upon x pi I. So what this means is that since we observe the parents, xi is only dependent of x pi I, and is independent of all its non-descendants, so which can be ignored in this particular joint probability or conditional probability distribution over here. Hence, we can see that in this statement over here, or this conditional probability, it means that we define a local parent-child relation as specified by the directed graphical model, and this directly corresponds to the arrow that is pointing. So if I have xi and x, the parents of xi, so all I need to do would be to look at the set of parents of xi in order for me to write down the factorized conditional probability distribution in this particular way here. So the locality of the parent-child relation is used to construct the economical representation of the joint probability distribution. What this means is that I can factorize a joint probability distribution into a product, here a joint probability distribution, into a product of conditional independence or conditional probabilities where each random variable is only conditioned upon its immediate parents. So from here, we can already see the difference between, suppose that we are considering all the random variable to be correlated with each other. Then we saw earlier that this will end up with a k to the power of n complexity in terms of the inference as well as the learning. But if we were to treat every random variable as independent, then we will end up with this product over here where everything becomes independent. But we saw that although this ended up with a linear complexity of nk, but this is not going to model the real situation or the real scenario well because of the loss in the relation between the random variables. So now we have strike a compromise in between the two, where we say that we neither take all the correlation between all the random variables nor treating everyone as independent. We saw in the example of Bart-Simpson's family tree that that random variable itself is only independent, is only directly dependent of its parents, and given its parents is conditionally independent of all other non-ancestor of that particular random variable, and hence we can rewrite them into this way. So in this case, all we need to do would be to model the number of the probability distribution within this factor, within this conditional probability itself, over n of this joint probability or conditional probability distribution, and the complexity is going to be somewhere in between k to the power of n multiplied by k. And here's a sketch of the proof for that the joint probability distribution can be rewritten as a product, or can be factorized into a product of all the random variables conditioned upon the individual random variables conditioned upon its immediate parents. We'll start off by rewriting the joint distribution here into this form over here by using the chain rule, where we can see that the first term is x1 by assuming that there is a topological ordering of the directed graphical model. What this means is that I assume that x1 has no parents, and then as I descend to the any graph over here to the next level, then I will label the random variable according to the topological order x2, x3 in the same level, and then I could have x4 in the next level, for example, then x5 in this level, and x6 in this level, for example. So each level over here, it means that it's going to be labeled topologically. And of course, I can also make this arrow here, but since they are all x4, x5, x6 are descendants of x2 and x3, then it will be in the same level over here. It need not be this. What this means is that this graphical model, it need not be a tree here. It's in the general form, but I'm just assuming the topological ordering of this. And by doing so, what I can do here is that I can rewrite this joint probability distribution in terms of the chain rule in this factorization over here. It's also important to note that despite that there is a product of the probability over here, the complexity to represent this factorization over here is still the same complexity which means that it still requires k to the power of n parameters to represent. The reason is because can be easily seen here. We can see that despite that we factorize this into this form, x2 conditional upon x1, and then all the way to p of x n conditional upon xn minus 1 and all the way to xn. So this table over here still requires k to the power of n number of parameters to represent it. But by assuming that we have the conditional independence, the parent-child relation that we have seen earlier on, we can see that despite the from this particular factorization following the chain rule over here, all these terms of in general pn xn conditional upon xn minus 1 all the way to x1 over here, we can see that some of the terms or many of the terms here, in fact it drops off because xn is only dependent, given its parents, it's conditionally independent of all the rest of the random variable in this expression over here. Hence, we can generally write it into every one of these factorized of these factors of the joint probability distribution over here. We can generally rewrite this into xi is only dependent on its parents, and it would become a product of all these terms over here. Hence, we reach this general expression that we have seen in the previous slide. An example over here. So given this Bayesian network over here, by following this rule that we have derived earlier, we can immediately write down the factorized form of the joint probability distribution of this graphical model, directed graphical model that consists of 6 random variables. So we can see that x1 there's no parent, so we will write down p of x1 multiplied by p of x2 conditional upon x1, because there is a direct arrow that points from x1 to x2, hence x1 is the parent of x2. And then we'll proceed on to look at x3, and since x3 it has an arrow pointing from x1, then it's this means that we need to condition it upon x1, as well as p of x5 conditional upon x3 and p of x4 conditional upon x2. Finally, it will be p of x6 conditional upon the 2 arrows that are pointing towards x6. This means that it has 2 parents, x2 and x5, and hence this would be the final joint probability distribution of x1 to x6 in a factorized form. You can verify that this is true, and it actually follows this equation, the general equation that we have derived in the earlier slide. So what this means is that it's very important that given any particular graphical model that looks something like this, a Bayesian network, I must be able to immediately write down the factorized form of the joint probability distribution that is inferred from this particular graphical model, and vice versa. This means that if I were to give you the joint probability, the factorized form of this joint probability distribution, we must be able to recover back or to draw this graphical model by looking at the factorized probability distribution here, which can be easily drawn. If we look at this here, so x1 there's no condition upon, there's no parents, we know that x1 is going to be independent, there's no parents to x1. And then we look at x2 is conditional upon x1, so we directly draw x2 over here and draw an arrow to that points from x1 to x2 and so on and so forth. What this also means is that if you still recall in the introductory lecture, I said that what does this graphical model tell us, or what does graphical model mean in one particular sentence? This means it actually means that we're trying to get global information. We're trying to get the global information, which is the joint probability of every random variable by just observations of local information. This means that we are looking locally. We are looking locally at every pair or every random variable that is pointed at by the set of parents. So this pointing of the set of parents simply means a conditional probability here in the local sense that we need to observe. Here's another example over here where given the this graphical model, given the graphical model or the joint probability distribution, we should be able to get the set of conditional independence by just reading off from the Bayesian network that is given to us here. So in a case where I'm given the factorized form of the joint probability, I must be able to draw this Bayesian network, which I have explained in the earlier slide. So from this Bayesian network, I should be able to read off from the Bayesian network, from the graph, the set of conditional independence over here. We can see an example. We can see an example over here that, for example, x3. We're interested in x3. So we can see that the non-descendants of x3, or rather the descendant of x3, are x5 and x6. So the non-descendants of x3 are naturally x1, x2, and x4. And given the parents of x3, which is x1 over here, we can see that x3 becomes conditionally independent of x2 and x4, given that we have observed x1, and we indeed notice that this is one of the conditional independence that is condition that's written here. So I leave all the rest, that you should be able to read off all the rest of the conditional independence by following these rules, the parent-child relationship that we have described earlier on. Here's another example to verify that x1 and x3 are indeed independent of x4 given x2. So we can directly see here from the example from the Bayesian network over here, the x1 and x3 over here, x1 and x3 over here, they are independent of x4 given x2. They are given x2 over here, it's independent of x4. What this means is that since x2 is the parent of x4 and x1, x3, they are non-descendants of x4. So once we observe x2, x1 and x3 becomes independent, conditionally independent of x4. So we'll do this by computing the marginal probability of this x1, x2, x3, and x4, and denoted by this guy over here. We'll prove that by computing the marginal probability that x4 conditional upon x1, x2, x3. Since the claim is that the x4 becomes independent of x1 and 3 given x2, then we can rewrite this into this particular form over here, where x4, given that we have observed x2, we do not need x1 and x3 anymore. But let's prove this by computing the marginal probability. So in order to do this, we have to compute two parts of the probability according to the conditional probability expression by writing this P of x4 conditional upon x1, x2, and x3. We can rewrite this as the joint distribution of x1, x2, x3, and x4 divided by the probability, the joint probability of x1, x2, and x3. So let's first look at the numerator on the computation of the numerator of this guy over here. So since the graphical model consists of 6 random variables, we need to, and we saw that the joint probability distribution that we are interested in here only consists of x1 to x4. So hence we need to marginalize away x5 and x4 from the joint probability distribution, which is, let's write this as marginalization of x5, marginalization of x6, given the probability of x1 all the way to x6, which is written over here. And then the next step that we need to do would be, we saw from the Bayesian network that this joint probability distribution can be factorized into this particular form over here, following the Bayesian network that is given here. And now what's interesting here is that we see that since we are doing the marginalization, the summation over x5 and x6, the two random variables of x5 and x6, and we can see that some of the factors over here, some of the factors of the probabilities over here, they're completely independent of x5 and x6. Hence, we can actually factorize, we can pull them out of this multiplication and the summation term over here. So after moving these four terms, which are independent of x5 and x6 out of the summation sign, we get this. We can push the x6 further in because we saw that this term here is independent of x6. And we can see that the summation of x6 conditional upon x2 and x5 is going to be 1. So this guy here is going to be 1, and we can remove this. Similarly, we can see that the summation of x5 conditional upon x3 is also going to be 1. So let me just briefly illustrate why this is going to be 1. Actually, this will end up to be a probability of x3 where it consists of two ones over here. So let me just illustrate this. Suppose that I have a binary state where x1 and x3, are going to take two states. x1 in general, xi is going to be in 0 or 1. So here it's going to be 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and then the joint probability or the conditional probability of x5 conditional upon x3, as we have seen earlier that in our earlier definition in the first lecture, in this kind of conditional independence or conditional probability over here, where I say that x5 is conditioned upon x3, when x3, so what this means is that x5 equals to 0 conditional upon x3 equals to 0 plus x5 equals to 1 conditional upon x3 equals to 0. You better sum up to 1 to make this a valid probability distribution. Similarly, x5 equals to 1 conditional upon x3 equals to 1. Or x5 equals to 0 conditional upon x3 equals to 1 plus x5 equals to 1 conditional upon x3 equals to 1, it better also sum out to 1. So what this means is that let's denote this as A, then this will become A, 1 minus A, and let's denote this B, this becomes 1 minus B over here. And if I were to sum over x5, what this means is that if I do a sum over x5 or px5 over x3, then this becomes the sum of x5 equals to 0 conditional upon x3 plus p of x5 equals to 1 conditional upon x3. And the full evaluation of this would be starting from this table here where I have 4 entries. I'll end up with 2 entries because after marginalizing out x5, I will be remaining x3 over here, which I know that x3 is going to take a binary state of 0 and 1. So this means that the marginalization of x5 away from this probability, the joint probability, the conditional probability over here, would mean that I need to, so let me write this here. The full evaluation would be, suppose that x3 equals to 0, then I would have to evaluate this term over here. x5 equals to 0, conditional upon x3 equals to 0, plus p of x5 equals to 1, conditional upon x3 equals to 0. And I need to find this number over here and put it here. And the second number would be x3 equals to 1. I need to evaluate this, x5 equals to 0, conditional upon x3 equals to 1, plus the probability of x5 equals to 1, conditional upon x3 equals to 1. I need to find this number over here and put it here. So we can see that since x5 equals to 0, conditional upon x3 equals to 0, x3 equals to 0 can be read over here. So this would be the first entry, it will be A, plus x5 equals to 1, conditional upon x3 equals to 0, which is this term over here. The sum of the two becomes 1. So this entry here is 1. And then the second entry here would be x5 equals to 0, conditional upon x3 equals to 1, which is B over here. And the second term over here would be x5 equals to 1 and x3 equals to 1, which is the last term over here. So it's b plus 1 minus b, and that will also be 1. Hence, I can ignore this particular term over here and simply make it a product of 1, because the probability of this is always going to be 1. I'll leave it to you to work this out to show yourself that the marginalization over x6 of this conditional probability over here is also going to be 1. But in this case, it would be equal to 4 ones. To help you a little bit into working this out, you need to first write down the probability distribution. So in this case, if it is a binary term, then I would have 8 states over here to 1, 1, 1. Okay, I will have 8 states over here to represent this probability distribution over here. So theta 1 all the way to theta 8 over here. Then, as I need to find the marginalization over this, what it means is that the marginalization over x6 of the probability of x6 conditional upon x2 and x5, then after I marginalize away x6, what I would end up with would be a probability table of x2 and x5. So I will remain, there will be altogether 4 terms over here, which I need to, this guy here will go in here, where I need to compute these 4 terms from the conditional probability table that is given to me earlier. And this can be evaluated over the 2 terms of the sum of the 2 states of 6. So I can write this, I can write it this way: x6 equals to 1 conditional upon x2 and x5 over here. So in this case, I will go through all the possible states of x2 and x5. So the first term here that I need to compute would be to fix x2 and x5 equals to 0, while I sum over all possible states of x6, which I can read off all the entries from this particular table over here. And similar, once we have computed this, we can evaluate that since this term, 2 summation term drops off, we will be remaining this term over here. And that would be the joint probability of x1, x2, x3, and x4. We can do similar things to compute the joint probability of x1, x2, and x3. This term here, which we can directly take it from here, since this is the joint probability of the 4 random variable, the joint probability of the 3 random variables would simply be the marginalization out of x4, and the joint probability of x1, x2, x3, and x4 over here, which can be directly taken from this expression over here. Then the next thing that we can see is that x4 conditional upon x2 is the only term with x4, so we can push the summation sign inside here and rewrite this as the probability of x1 multiplied by x2, x1, x3, x1 sum over x4, and the joint conditional probability of x4, x2 over here. So since this is a probability of x4 conditional upon x2, we can also conclude that this sums to 1. Hence this drops off, and we are left with this particular term over here. And finally, we compute the conditional probability, as we have mentioned earlier, by taking the joint probability of the 4 random variables divided by the joint probability of these 3 random variables over here. And we can see that these terms over here all cancels off, except for x4 condition upon x2. And hence, we conclude that the x4 is indeed conditionally independent of x1 and x3, given that we have observed x2 over here. And we can see that there is indeed a parameter reduction after taking only the parent-child relation in the conditional probability representation to factorize the joint distribution. Let us use mi to denote the number of parents of the node xi, and each node takes on k value. So the conditional probability associated with this node can be rewritten as k to the power of mi plus 1, because they are all correlated to each other. So what this means is that I have xi over here and then I have n number of parents that points towards xi over here. So all this set of locally dependent random variables, they would have to be all incorporated into a particular probability table. Let's say if there's k values per random variable, then altogether I will have k to the power of mi plus 1, which is that node itself. And this would result in a huge reduction of the parameters that is needed to represent our joint probability, considering the conditional independence right now. So and we can see that this will be a reduction of k to the power of n to k to the power of m plus 1, where n here represents all the total number of the random variables in the graphical model, whereas m plus 1 over here, it represents the local independence, the parent-child relation, where m is a lot lesser than n. So here's an illustration of the total number of parameters that is needed to represent this particular graphical model, or the Bayesian network that we saw earlier. So in this case, x1, suppose that each one of these random variable is only a binary state. We can see that x1, it has no parents. So this means that two parameters is enough to represent this probability table, because we are only interested in probability of x1 equals to 0 or the probability of x1 equals to 1 over here. And similarly for x2, there is a parent, which is x1 over here, since the probability distribution is x2 conditioned upon x1 over here. So since there are two random variables over here, we can write this as a probability table of x1, x2, 0, 0, 0, 1, 1, 0, and 1, 1 over here. And this would be the probability distribution, the probability number of x2 conditioned upon x1. And it's also interesting to reiterate that since this is a conditional probability, then these values over here, these two values over here, conditioned upon x1, where x1 are the same state over here, then this must sum to 1, and this here must also sum to 1. So we can see that x6, for example, over here, it has two parents. Then this would be require a more parameter to represent the conditional probability of x6 conditioned upon x2 and x5. We will need altogether x2, x5, and x6 over here. So altogether we will have 8 number of parameters to represent this locally. But despite this, the total number of parameters in the factorized version over here is still far lesser than the naive way of correlating every random variable in the joint probability distribution. So here we see that in total we will only need 26 parameters, and comparing this with the total number of parameters that we need for the full joint distribution, or naive way of the joint distribution, which will be 2 to the power 64 parameters, which is already a lot lesser than 64. And we can I'll leave it to you to prove it to yourself, or to show some examples for yourself, that this difference becomes more significant when n, the total number of parameters, becomes larger. So it turns out that there are additional conditional independences that we can read from the graphical model, in addition to the ones that we can read off from the parents-child relation. And an example here is that it turns out that x1 is also conditionally independent of x6, given that we have observed x3 and x2 over here. But this doesn't follow the rule of the parent-child relation, where x6 here, we can see that x6 here is not a non-descendant of x1, it's in fact a descendant of x1, but it still can be conditionally independent of x6, given that we have observed x2 and x3. which are not the parents of x1. The proof can be shown here. Again, we want to compute this guy over here. So when we say that x1 is conditionally independent of x6, given that x2 and x3, then what we want to prove is that by writing the conditional probability here, x1, x2, x3, and x6. So since we are given x6, we do not need x2 and x3 anymore because they are conditionally independent. We want to show that this relation is indeed true over here. So we'll start off by rewriting this probability distribution, the conditional probability distribution in this form over here, following the conditional probability rule. And the next thing that we need to do would be similar to the previous example, to find what's the numerator as well as the denominator in order to evaluate this. Let's start by looking at the joint probability of x1, x2, x3, and x6. So here, since we notice that x4 and x5 are missing from this joint probability distribution, it means that we have to start off by marginalizing off x4 and x5 from the full joint probability distribution of x1 to x6 over here, which we can then rewrite this joint probability distribution into the factorized form following the parent-child relation that can be read off from the Bayesian network. We can see that this becomes this term over here, and similarly we can rearrange this part here and see that and observe that some of the terms here are indeed independent of x4 and x5, which we can bring to the left side of the summation sign as illustrated in this step over here. So we can see that x4 over here, conditional upon x2, is independent of x5. Hence x5 has to be pushed further in, and where the remaining two terms here are dependent on x5, and then we would have a term of x4 over here, which we need to put it associate it with the summation, the marginalization of x4. And again, this is a marginalization of the probability of x4 conditional upon x2, which will sum up to 1, and we can cancel this away. We can drop this term over here. But in general, the marginalization of x5 over here is not going to be equals to 1. So hence this term must remain over here. Next, we move on to look at the denominator term, where we find that x1 is missing here. x1, x4, and x5 is missing here. So we need to marginalize away these three terms over here. We do the same thing. We marginalize over x1, x4, and x5 over the joint probability distribution, which can be rewritten into this form from the Bayesian network. And then we saw that this step here, x4 and x5, is exactly the same as before, where we can push in x4 and x5 over here and cancel off x1. Then we are remaining with this term over here, these two terms, these two summation over terms over here, which we cannot further evaluate. And the final thing would be to take this expression over here, and divide by this particular expression over here, which we see that the sum of marginalization over 5 can be cancelled off over here. So what we are left off would be this particular expression over here. But what's interesting here is that since we only left with x1, x2, and x3 in this in the numerator over here, and we saw that x1, x3, x2, x3 appearing in the beginning of this graph over here, we can rewrite this term because this term here directly follows the joint distribution, the factorization of this joint distribution. It forms a subgraph over here, and we can rewrite it into the joint probability of x1, x2, and x3. And then it's the same thing for the denominator. We can rewrite this into the joint probability of x1, x2, x3. And since we are marginalizing out x1, we can rewrite this as the joint probability of x2 and x3 by eliminating away x1 in the denominator over here, which we can rewrite this into the conditional probability of x1 conditional upon x2 and x3. Hence we have proven that the relationship over here is correct. So having observed that there are additional conditional independences that cannot be directly described by the parent-child relation, the question is that can we find another method to directly allow us to detect or to figure out which are the additional sets of conditional independence from the Bayesian networks without going through the tedious computational process that we have worked out earlier in this example? The answer turns out to be yes, and we can do this by observing the graph structure where some nodes are being, the paths from one node to another is being blocked by a set of nodes which are directly observed. So here, for example, the example that we have looked at earlier on here, that x1 is conditionally independent of x6, given that we have observed x2 and x3 over here. We can see that if we observe x2 and x3 over here, this means that there is a block of the path. That means that we cannot traverse from x1 to x6 in all possible directions over here. And this means that x6 and x1 becomes conditionally independent, given that we have observed x2 and x3 over here. But we have to be very careful about the notation of blocking. So for example, x2 is not independent of x3, given that we have observed x6 as denoted by the notation of blocking. So in this case here, because of this unique structure, which we will see in a few more slides, that this is the head-to-head structure, that by observing x6 over here, indeed it doesn't mean that x2 and x5 becomes conditionally independent. It's actually the other way around. It actually makes x2 and x5 conditionally dependent on each other. So we'll look at the precise definition of blocking through the three canonical three-graph representation, which is otherwise known as the D-separation principle. And in the first case of the three canonical three-node graphs in the D-separation principle, we see that we are given three nodes A, B, and C, and they are linked in this way, where A is pointing towards C and B and C is pointing towards B. So the joint distribution of this graphical model is given by this factorization over here. So A has no parent, so we write probability of A, C conditional upon A, and B condition upon C. So these are the three terms of the factorization of the joint probability distribution of A, B, and C. In general, if none of the random variables are observed, we can see that A and B are not independent by marginalizing over C. So we can see that the joint probability distribution of this can be obtained. So joint probability distribution of A and B can be obtained by marginalizing over C over A, B, and C, which can be rewritten here using the factorized version from the graphical model. And by substituting this term inside here, we can see that A is independent of C. We pull it out. It works out to be B condition upon A, and in general this is not equals to PA multiplied by PB. So this means that A and B are not independent, given that we observe none of the random variables over here. So in the case where we observe the random variable C over here, we can see that A and B, the random variable of A and B, would become conditionally independent. We start off from the conditional probability of A and B conditional upon C. We can rewrite this into this form over here, and we can see that the numerator can be directly substituted with the factorized joint probability of the graphical model that is given here, which is in this particular form. And following Bayes' rule, which means that we can rewrite this numerator term over here into this term over here, that we can cancel off C. Then we finally obtain the probability of A conditional upon C multiplied by the probability of B conditional upon C. This means that once we observe C, A and B, the random variable of A and B of this canonical graph is going to be conditionally independent. And hence we say that this is once we observe C, the path from A to B is blocked. And we also call this kind of canonical graph here the head-to-tail structure, where in this case we can see that the arrowhead is pointing towards C, and the tail of the arrow is coming out of C. Hence we call this a head-to-tail structure. And such a path that connects nodes A and B renders them dependent if C is not observed. This means that the path can be is connected from A to B as well as from B to A when C is not observed. But when C is observed, then we say that the path from A to B and B to A is blocked, or rather the observation of C blocks the paths from A to B and vice versa. And this is the independence property, the first independence property that we can derive from the d-separation principle. An intuitive interpretation or an example over here would be that A is past, C is present, and B is future. So normally when we observe the present, we say that the future is only dependent on the present and is kind of independent of the distance past. This is true when we are looking at weather forecast, for example. In a naive weather forecast model, we will see that we always predict the current temperature or the current weather according to what we observe in the immediate past. And this is a classical example of a first order Markov chain. We'll look at Markov chain and hidden Markov chain in more detail when we look at the hidden Markov model as well as the MCMC sampling lecture. A second example of the canonical graph is this particular structure over here, where we have C, random variable C pointing towards A and B, and we'll see that we call this the tail-to-tail structure. The tail-to-tail structure because the two tails of the arrow are pointing out of the random variable C. And the joint distribution, the factorized joint distribution of this graphical model here is given by this expression over here. So in general, if none of the random variables are observed, then A and B are not independent. We can see this by writing the expression here. The joint probability of A and B, they are not independent if we marginalize off the joint probability of A, B, and C, marginalize over the random variable of C over here. We can see that in general we cannot evaluate this term further, where A and B is still dependent on the random variable of C. But if we observe C over here, the random variable C over here, we can see that this A and B, the random variables A and B, becomes conditionally independent. We'll show this by evaluating this term over here, the conditional probability that we have seen earlier, and this can be rewritten into joint probability of A, B, and C divided by C. So we substitute this term over here with the graphical model, the factorized probability of the graphical model divided by C. We'll see that C cancels out, and we are left with these two terms over here, which means that conditional upon C, A and B becomes conditionally independent. Now, as I've mentioned, that this canonical structure over here is called the tail-to-tail structure with respect to the path from node A to B, and when C is not observed, then there is a path that exists from A to B and vice versa, and hence A and B is not conditionally independent given that we don't observe any random variables over here. When C is observed, then we say that the path from A to B and B to A, they are blocked. So in this case here, we will use this as a conditional independence property. Intuitive interpretation of this would be the chronological edge used to represent the random variable C, as well as the shoe size, which is represented by the random variable A, and the amount of gray hair that one person can have, represented by the random variable B. So given the fact that we don't observe the chronological edge of the person, then we would have no knowledge on the shoe size and the gray hair. So it's very intuitive to say that the shoe size will be larger, and given that the amount of gray hair is more, and vice versa, if we don't observe the chronological age of the person. But as long as we observe the age of the person, once we've observed the age of the person, then we will say that the shoe size becomes independent of the amount of gray hair. We do not need to care about the gray hair to infer the shoe size. The two random variables becomes conditionally independent once we know the age of the person. So we say that, in other words, we say that the random variable C explains all the dependence between A and B. And since C explains all the dependence between A and B, then given that we have observed C, A and B becomes conditionally independent.